welcome to this problem walkthrough. In this session, we'll explore problem number 2148, count elements with strictly smaller and greater elements. Together, we'll break down the problem, examine potential approaches, and analyze their efficiency. Let's dive in. The problem requires us to work with an integer array called nums. A number in this array is considered special if it meets two conditions. First, it must be strictly greater than the smallest number in the array, and second, it must be strictly smaller than the largest number in the array. In simpler terms, a number is special if it lies strictly between the minimum and maximum values of the array. Our goal is to count how many such special numbers exist in nums. The input will always be a single integer array, where the size of the array is between 1 and 100, and each element can range from -100,000 to +100,000. The output will be a single integer, representing the count of these special numbers. Let's look at the first example to understand this better. Here, the input array nums is 11, 7, 2, 15. The smallest value in the array is 2, and the largest value is 15. To find the special numbers, we identify the elements that are strictly greater than 2 and strictly smaller than 15. In this case, the numbers 11 and 7 satisfy these conditions. Therefore, there are exactly two special numbers in this array, and the output is 2. In the second example, the input array is -3, 3, 3, 90. The smallest value here is -3, and the largest value is 90. The numbers that are strictly greater than -3 and strictly smaller than 90 are the two occurrences of 3. Even though 3 appears multiple times, we count each occurrence individually since the problem does not require us to count unique values. Hence, the output in this case is also 2. Now consider the third example, where the input array is 1, 1, 1. In this case, the smallest and largest values are both 1. Since there are no numbers that are strictly greater than the minimum or strictly smaller than the maximum, there are no special numbers in the array. As a result, the output is 0. This example highlights that if all elements in the array are the same, it is impossible to have any special numbers. Finally, let's discuss some constraints and edge cases. The array can have between 1 and 100 elements, with each value ranging from -100,000 to +100,000. For edge cases, if the array contains only one element, such as nums equals 5, the output will always be 0 since we need at least two distinct values to satisfy the conditions. Similarly, if all elements in the array are identical, like nums equals 4, 4, 4, the output is also 0. On the other hand, if the array includes extreme values, such as nums equals -100,000, 0, 100,000, only the middle element, 0, qualifies as special. Lastly, if there are repeated non-special numbers, such as in nums equals 1, 2, 2, 2, 3, all three occurrences of 2 are counted individually, leading to an output of 3. To solve this problem, one intuitive approach is the brute force method. The idea here is simple. For each element in the array, check if there is at least one element that is smaller and one that is greater. This can be done using two nested loops. The outer loop selects an element, and the inner loop iterates through all other elements to verify the conditions. If both a smaller and a greater element exist, we increment the count. While this approach is straightforward and easy to understand, it has a significant drawback. It involves iterating through the array multiple times, resulting in a time complexity of n squared. This makes it highly inefficient for larger arrays, even though the implementation is simple and intuitive. For bigger datasets, this inefficiency can become a major concern, so we need to explore alternatives. A more efficient approach leverages the observation that an element can only have both smaller and greater elements if it lies strictly between the smallest and largest values in the array. Using this insight, we can eliminate the need for nested loops. First, we find the minimum and maximum values in the array. Then, we iterate through the array once more to count the elements that are strictly greater than the minimum and strictly less than the maximum. This process has a linear time complexity of n, as finding the min and max takes n, and iterating through the array again also requires n. Not only is this approach much faster than brute force, but it's also easier to implement than some other alternatives, making it a strong candidate for solving the problem. Another method worth considering involves sorting the array. When the array is sorted, the smallest and largest elements are easily identifiable. With this setup, counting the elements that lie strictly between the smallest and largest becomes straightforward. After sorting, we can directly determine the range of valid elements without additional nested iterations. However, sorting the array introduces a time complexity of O(n) log n, which is less efficient than the O(n) approach but still better than the O(n) squared brute force method. A potential downside of this approach is that sorting modifies the original array, which may not be desirable in certain scenarios. While it's a practical alternative, it's generally not the most optimal choice for this problem. The best strategy for this problem is the optimized approach that uses the minimum and maximum values. This method is preferred because it achieves the highest efficiency with a time complexity of O(n). Additionally, it avoids modifying the input array, which can be an advantage in situations where the original order of elements matters. The simplicity of this solution also makes it easy to understand and implement. The key insight, that only elements strictly between the smallest and largest values are valid, helps to significantly simplify the problem. By focusing on these elements, we bypass unnecessary computations and ensure the solution is both scalable and elegant. This approach strikes the perfect balance between efficiency and clarity, making it the ideal choice for tackling this challenge. In this problem, the goal is to determine if there exists an element in the array that is neither the smallest nor the largest, essentially, an element that has at least one smaller and one greater value in the array. The brute force approach to solve this problem involves iterating through each element of the array and checking if there are smaller and greater elements relative to it. To do this, we use a nested loop structure. For each element in the array, we initialize two flags, has smaller and has greater, to track whether we find a smaller or greater value during the inner loop. If both flags are set to true for any element, we can immediately return true since such an element exists. If no such element is found after testing all elements with this approach, we return false. While straightforward, this method involves iterating through the array multiple times, making it computationally expensive as the array size grows. The brute force approach, while simple, is inefficient because it uses nested loops, resulting in a time complexity of O(n) squared. To optimize this, we can leverage the properties of the smallest and largest elements in the array. Specifically, we know that the smallest and largest elements can never meet the condition because they lack both smaller and greater neighbors. In the optimized approach, we first identify the smallest value, min_val, and the largest value, max_val, in the array. This requires just one pass through the array, taking O(n) time. Next, we make a second pass through the array and check if any element is strictly greater than min_val and strictly less than max_val. If such an element is found, we return true. If the iteration completes without finding such an element, we return false. This approach is much more efficient, as it eliminates the need for nested loops and achieves a linear time complexity of O(n). Now, let's consider some key insights and edge cases. If the array has fewer than 3 elements, it is impossible for any value to meet the condition, so the answer is always false. Similarly, if all elements in the array are the same, no element can be strictly smaller or greater than another, meaning the result is also false. The optimized approach works because the smallest and largest elements in the array are the only values that cannot satisfy the condition. By identifying and excluding these two extremes, we can efficiently test the remaining elements. Regarding data structures, both the brute force and optimized approaches rely on simple array traversal, and the optimized approach uses variables like min_val and max_val to store the smallest and largest values, which eliminates the need for nested loops and streamlines the process. Comparing the two approaches highlights the trade-off between simplicity and efficiency. The brute force method has a time complexity of O(n) squared due to its nested loops, making it impractical for large arrays, though it has a space complexity of O(1), since no additional data structures are used. The optimized approach, on the other hand, brings the time complexity down to O(n) by leveraging the properties of the smallest and largest elements in the array. It also maintains a space complexity of O(1), making it both faster and more scalable. This comparison underscores the importance of understanding the problem's constraints and using problem-specific insights to design efficient algorithms. This solution efficiently counts the elements in the array that are strictly greater than the minimum value and strictly less than the maximum value. We start by finding the minimum and maximum values in the array using the min and max functions, which operate in O, n, time. Then, we iterate through each element in the array and check if it lies strictly between the minimum and maximum values. If it does, we increment a counter. Finally, we return the count. This approach ensures that the solution runs in O, n, time, where n is the size of the input array, making it efficient for large inputs. Here, we begin by defining a class called solution and implementing the method countElements, which takes an integer array, nums, as input. The goal is to count how many elements in the array are strictly greater than the minimum value and strictly smaller than the maximum value. First, we initialize two variables, minval and maxval, to store the smallest and largest values in the array. We set minval to integer.max_value and maxval to integer.min_value as initial placeholders. Then, we use a for each loop to iterate through each number in the nums array. Inside the loop, we compare each number to minval and maxval, updating them whenever we find a smaller or larger value, respectively. This ensures that by the end of the loop, minval and maxval hold the minimum and maximum values of the array. Next, we initialize a counter variable, count, to 0. This will keep track of the elements that meet our criteria. We loop through the nums array again, and for each number, we check if it is greater than minval and less than maxval. If both conditions are true, we increment the count. By the end of this loop, count will hold the total number of elements that are strictly between the minimum and maximum values. Finally, we return count as the result. This straightforward approach ensures that we process the array efficiently while maintaining clarity in the logic. Here, we are solving the problem for the input array nums equals 11, 7, 2, 15. The first step is to find the minimum and maximum values in the array. In this case, the minimum value is 2, and the maximum value is 15. These values help us identify the range of numbers we are interested in. Next, we initialize a counter, starting at 0, to keep track of elements that fall strictly between the minimum and maximum values. We then iterate through each element in the array and check if it satisfies the condition min_val number max_val. For 11, the condition evaluates to true, so we increment the counter to 1. Similarly, for 7, the condition is also true, so the counter increases to 2. However, for 2, the condition is false because it equals the minimum value, so the counter remains 2. Finally, for 15, the condition is false because it equals the maximum value, meaning the counter does not change. After completing the iteration, we return the final count, which is 2 in this example. Now, let's look at the input array nums equals 1, 1, 1, 1. The first step is again to find the minimum and maximum values. Here, both the minimum and maximum values are 1, since all the elements in the array are the same. With the range defined, we initialize the counter at 0 to track elements that strictly lie between the minimum and maximum values. As we iterate through each element in the array, we check the condition min_val number max_val. For every element 1, this condition evaluates to false, as no number can be strictly greater than 1 and strictly less than 1 simultaneously. As a result, the counter remains unchanged at 0 throughout the iteration. Finally, we return the counter, which gives us an output of 0 for this example. For this example, we are working with the input array nums equals 3, 6, 6, 6, 9. The first step is to determine the minimum and maximum values. Here, the minimum value is 3, and the maximum value is 9. With this range established, we initialize the counter at 0 to track numbers that fall strictly between 3 and 9. As we iterate through the array, we evaluate each element against the condition min_val number max_val. For the first element, 3, the condition is false because it is equal to the minimum value, so the counter remains 0. For the next element, 6, the condition is true, so we increment the counter to 1. The following two elements are also 6, and both satisfy the condition, so the counter increases to 2 and then to 3. Finally, for the last element, 9, the condition is false because it equals the maximum value, leaving the counter unchanged. After completing the iteration, the final count is 3, which we return as the output for this example. To determine the time complexity of our solution, we break it into two main steps. First, we find the minimum and maximum values in the array using min, nums, and max, nums. Each of these operations requires iterating through the entire array once to locate the smallest and largest values. Since they are independent operations, their combined time complexity is O(n) plus O(n), which simplifies to O(n). Next, we count how many elements lie strictly between the minimum and maximum values. This involves another full traversal of the array, where we check each element against the previously calculated bounds. Like the first step, this counting operation has a time complexity of O(n). When we combine these two steps, the total time complexity of the solution becomes O(n) for finding the bounds plus O(n) for the counting step, resulting in an overall time complexity of O(n). Now, let's analyze the space complexity of the solution. The algorithm operates with an O(1) space complexity because it does not use any additional data structures like arrays or hash maps. Instead, it relies on a few simple variables to store intermediate values, such as min_val, max_val, count, and number. These variables occupy a constant amount of space, regardless of the size of the input array. Additionally, the input array nums is accessed directly during the computations, so no extra space is allocated for processing. For these reasons, the space complexity of the solution is constant, or O(1). Furthermore, the time complexity remains O(n) across all scenarios, best, average, and worst cases, because no matter the array's contents, the algorithm always performs a complete traversal to find the bounds and count the elements between them. Let's compare the optimized solution to a potential naive approach. A brute force method might involve comparing each element with every other element to determine whether it is strictly greater than the minimum and strictly less than the maximum. This would require (n² comparisons for an array of size n, as each element would need to be checked against every other element. In contrast, the optimized solution leverages the min and max functions to determine the bounds in O(n) time and performs a single traversal to count the valid elements. This reduces the time complexity to O(n), which is significantly more efficient than the (n² complexity of the brute force approach. This efficiency becomes particularly important for large arrays, where the difference in performance between O(n) and O(n² is substantial. Finally, let's summarize the mathematical reasoning behind the big O analysis. The min and max functions each require a full scan of the array, contributing O(n) time complexity. Similarly, the counting loop iterates through the array once, adding another O(n). When we combine these two operations, the total time complexity becomes O(n) plus O(n), which simplifies to O(n). In big O notation, constants are ignored, so the overall time complexity remains O(n). On the other hand, the space complexity is O(1), because no additional data structures are used, and memory usage remains constant regardless of the input size. These characteristics make the optimized solution both time efficient and space efficient, ensuring it performs well even for large input sizes. One common mistake when solving this problem is not accounting for edge cases. For example, if the array has fewer than 3 elements, such as being empty, containing a single element like 1, or just 2 elements like 1, 2, it becomes impossible for any element to have both a strictly smaller and a strictly greater counterpart. To prevent this, implement a check at the beginning of your code to handle these cases explicitly, ensuring your logic doesn't break. Another issue is overlooking duplicates. In arrays like 3, 3, 3, all elements are the same, so there are no distinct smaller or greater elements. Your solution must be designed to handle duplicates properly, especially when counting elements that need distinct comparisons. Additionally, a naive brute force approach using nested loops can lead to inefficient time complexity of O(n², which becomes impractical for larger inputs. To optimize, consider approaches like sorting or pre-computations that can reduce the time complexity to O(n log n, or even O(n) in some cases. Another common pitfall is using incorrect bounds in your comparison logic. Misinterpreting the requirement for strictly smaller or greater elements and instead using non-strict comparisons, such as equals or equals, can lead to incorrect results. Always ensure you implement the strict inequalities and as specified in the problem. Sorting the array can help simplify finding smaller and greater elements, but it introduces its own challenges. For instance, if you sort the array, you must be careful to manage indices and duplicate values correctly, as sorting changes the original order. Mapping back to the original indices or explicitly handling duplicates can help you avoid bugs when using this approach. When tackling this problem in interviews, there are a few key points to keep in mind. First, clarify the problem requirements up front. Ask whether the array elements are guaranteed to be distinct or if duplicates are allowed. This distinction significantly affects your implementation and edge case handling. Next, demonstrate optimization awareness early. If the brute force solution with O and squared complexity is too slow, explain alternatives like sorting or using prefix and suffix arrays. This shows a clear understanding of efficiency. Additionally, recognize that this problem often aligns with common patterns in array-based problems, such as searching for elements smaller and greater than a target. Identifying the pattern and referencing similar problems, like subarray sums or triplet checks, can help guide your thought process. Finally, communicate trade-offs effectively. For example, if you propose an O n log n sorting-based solution instead of an O n squared brute force approach, explain why it's better for larger inputs and the trade-offs involved in terms of readability or implementation complexity. This problem also has connections to several related problems, which can provide valuable context and practice. For example, LeetCode 611, valid triangle number, involves finding the number of triplets that can form a triangle, which requires similar comparisons of smaller and greater elements. Another is LeetCode 628, maximum product of three numbers, where you sort the array to identify the largest and smallest elements for calculating the maximum product. LeetCode 16, threesome closest, introduces constraints on the sum of triplets and emphasizes optimization techniques like two-pointer approaches. Finally, LeetCode 334, increasing triplet subsequence, is a variation that asks for a subsequence of three strictly increasing numbers, solvable in O, n, time. These problems share overlapping concepts, and practicing them can deepen your understanding of core strategies like sorting, two-pointer techniques, and prefix/suffix computations. There are several approaches you can use to solve this problem, each with its own trade-offs. A sorting-based approach is a straightforward option. By sorting the array first, you can easily identify whether each element has a smaller element on its left and a greater element on its right. This method has a time complexity of O n log n due to sorting and is simpler to implement, but it modifies the order of elements, which might not always be desirable. Alternatively, you can use prefix and suffix arrays. Pre-compute the smallest element to the left of each index and the largest element to the right. Then, for each element, check if it lies between its corresponding prefix and suffix values. This approach achieves O n time complexity but uses extra space for the prefix and suffix arrays. Finally, the most efficient method is a one-pass linear scan. Maintain two variables while iterating through the array, one for the smallest element seen so far and another for the largest element after the current index. This approach runs in O n time with O1 space, making it the fastest and most space efficient, though it can be harder to implement correctly under time constraints. Great job! We've reviewed the problem, analyzed our solutions, and discussed key takeaways. Remember, consistent practice is key to mastering algorithmic challenges. Thanks for watching, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!